My name is Peter Hunt.
Hi, I'm Mrunal Patel. I'm a principal engineer at Red Hat. I'm a maintainer of runc, the OCI runtime spec, and CRI-O.
And I also work for Red Hat software engineer. I maintain CRIO and also Podman and some other related container technologies. And today we're here to talk to you about CRIO. So if that's not what you want to listen to, you should probably leave. So here we are, CRIO, all the runtime a container needs. So this is an introduction talk. So let's do an introduction. What is CRIO? What do we mean by CRIO? So CRIO is a two-part acronym. So the first part of it, CRI, stands for the Container Runtime Interface. The Container Runtime Interface is the way that the kubelet asks a runtime to create containers, pull images, create pods, and the like. So for a bit of a history lesson, in the beginning, there was just Docker, and the kubelet directly talked to the Docker socket, asking it to create containers for it. Then came along Rocket, and the entire, so Rocket is another a CoreOS runtime that worked with Kubernetes, and the way that they implemented it in the kubelet was they said, if we're using Rocket, then execute the Rocket method. Otherwise, execute the Docker method. And then came along some other VM-based technologies. And then the kubelet maintainers were like, whoa, wait, OK, let's slow down. So they created the CRI, the Container Runtime Interface. And basically what it does is it asks a container runtime to fulfill all of the needs that the kubelet has for a container runtime. So the CRI defines how implementations ask for, kubelet asks them to create a container, or create a pod, or pull an image, exec into a container, all of these various things. So CRI-O is an implementation of the Container Runtime Interface. What kind of implementation? An OCI compliant one. So that's what the O stands for, is OCI. So the OCI is a standards board that, and a set of projects that standardizes the way that containers are run, container image formats and the like. So the OCI was a good way to kind of make a basis for container technologies that other container managers and runtimes build on top of. So CRI-O supports all kinds of OCI compliant container images, including the legacy Docker one. Supports any container registry and protocols that the OCI defines between runtimes and registries, and it supports all OCI container runtimes. So we have runc, we have kata, and we run integration tests against both of those. There's C-run that someone in Red Hat is developing. We got gvisor. All of them, CRI-O will run with, and you can specialize your container needs there. So that's an introduction. The question then follows, why would I use CRI-O? What kind of value proposition does CRI-O give? So the number one thing that we like to say that is great about CRI-O is it's only for Kubernetes. So other container runtimes have a lot of different masters that they have to serve. They have there are clients that want to build containers. There are clients that want to push containers to container registries. But the kubelet doesn't need to do any of those things. And thus, neither does CRI-O. So CRI-O is only built for Kubernetes. CRI-O is Kubernetes only lover, as we like to say. Or the other way around. Kubernetes is CRI-O's only lover. As such, we can do things like run the entire Kubernetes end-to-end conformance suite against CRI-O for every PR merged, so that we're guaranteed to be conformant with the way that Kubernetes expects a runtime to act. We also run against the CRI tests and also our own integration tests, so we run like a ton of tests. It's crazy. It takes a long time before anything gets merged. This also, us being we version ourselves in lockstep with Kubernetes, which simplifies a developer's choice or an admin's choice to use CRI-O. With other runtimes, the question sometimes becomes, what version of X runtime works with Kubernetes 1.x? And you never have to ask that question with CRI-O. It's always going to be Kubernetes 1 16 works with CRI-O 116, and so on. So that makes it easier. And basically, the intention with CRI-O primarily is to make running containers in production boring and secure. And we'll talk a little bit more about secure in a little bit. But the boring aspect is because CRI-O only works with Kubernetes, you can expect CRI-O to run precisely with the way that the CRI expects in a reliable manner. And you can choose to use CRI-O, deploy it, and forget about it. We kind of like to liken using CRI-O in production as choosing XFS for the file system on your node. You make that decision once, and then you forget about it until, unless it breaks, which we like to say we don't really want to do. But that's, you're not really like fussing over the decision after day one. And we like to keep CRI-O that way. Another reason why to use CRI-O. So CRI-O is built off of the standard components. It's OCI compliant, which allows us to use some different tools that we work with to so it's compatible. So we have our container storage library that manages, so when you create a container, you have to slap it down on disk in a copy on write style so that you have your lower and merge DIRs to be shared among all these different containers, and the upper DIRs where you write to. Container storage manages that on the file system. You don't need a daemon to do that. Containers image is used for pulling images from registries and is able to pull from any sort of container registry in a lot of different formats and the like. We had supporting mirroring between registries and all of this. We use CNI, de facto standard for container networking now for all of our networking, so we don't re-implement the wheel with this. CNI has definitely dominated the space. So any CNI plugin that you want to use, you can plop right into CRI-O and it just works. And we support any OCI runtime. So any container runtime that you want to use, if, for instance, we test against Kata, so you can run your Kata VMs or your Kata containers inside of a VM with CRI-O, and it just works as expected. Why would I use CRI-O? It's a minimal daemon. Has anyone ever met this character? It's lived in a couple of different talks. How about this devilish figure? So here's Dan Walsh. He's been going on. He's currently occupying the booth where we've left, from which we've left. But he has, for a couple of years, been on a tirade against big, fat container daemons, ones that take over the entirety of the container space and do everything under the sun for a container. You don't need that. You don't need a container daemon to be able to write onto a file system in a certain manner, or to pull a tarball and then put it onto a disk, using HTTPS. So CRI-O is only for the CRI, and it's as little of a daemon as possible for the CRI. So it uses it, and an example of that is for all of our, so for instance, for CRI-O, all of the containers that run under it are actually only managed by CRI-O. They're not child processes of the CRI-O daemon. So that allows us to do things like restart the daemon with containers running, and those containers aren't disturbed because CRI-O is not their parent. There's a monitor process that CRI-O talks to, and we'll talk about that a little bit when we get into architecture. But CRI-O is not a monolith daemon. It's just exactly what the kubelet needs and nothing more. And finally, we are security focused. So another thing that Dan Walsh has always pushed is security, and really push container security. Who here has SC Linux enabled? Ooh, that's awesome. I'm not actually sure I do. Sorry, Dan. So CRI-O has been designed to be secure by default. So CRI-O will take a container process and give it a SE Linux label if it wasn't specified, and that allows us to prevent if you mount a volume into the host and the container isn't really expected to be able to do much with it, like we're going to block you there. Because from SE Linux standpoint, that's a process breaking out of its desired needs. We ship by default pretty low PIDs limits, so that 1024, so that and it's a lot. You can adjust the PIDs limit in CRI-O directly to prevent fork bomb attacks, for instance. We ship with as few capability, Linux capabilities as possible. Other container runtimes, for instance, give make node and net raw because they have to fulfill every single use case that exists under the sun for running and playing with containers. But CRI-O doesn't need to run with or play with containers. It's only for using them in production. So it has a lot fewer capabilities that it needs. And finally, oh no, actually that's it. Well, and it's by being a minimal daemon and only fulfilling the CRI, it also has a lower attack surface as such. So there's a lot of vulnerabilities that come into copying content into a container, and CRI-O can't do that. So there's no possibility of that happening. So we're now going to go a little bit into the architecture of CRI-O. So what happens is the kubelet talks over gRPC to the CRI-O daemon, and the CRI-O daemon then responds, takes the according action and then responds. There are two parts of the CRI that CRI-O obviously implements. There's the image service, which is responsible for pulling and listing images and deleting them, not pushing, because kubelet doesn't need to do that. And that's all managed through containers image. And then there's the much more exciting part of it, the runtime service, which actually gets into the nitty-gritty of how to use containers. So it's, run this pod and create this container and exec into this container. All of this is, so the runtime service manages this. To create a container, we use the OCI generator. So we create our config blob, and that config is then passed to a runtime and run. CRI-O uses the CNI to set up all the networking for inside of the pod and for outside of the pod if you're talking to the host network or if you're just a container talking to your own network. Use CNI for that. And then, so I'm going to shift gears a little bit and then talk about the pod architecture in CRI-O. So a CRI-O pod usually consists of an infra container, which is used to pin the Linux namespaces, though we're moving away from that model. But we'd still need it to pin the PID namespace to act as PID1 inside of the PID namespace and reap the processes that, like if a container dies, we don't want that to be a zombie process. Each container inside of a pod has a conmon instance, and conmon is the secret sauce to allow CRI-O to be a minimal daemon. Conmon is a monitoring process that actually is responsible for listening to the container. So conmon is responsible for keeping the standard in open if we need to exec into the container. It's responsible for writing all of the standard out and standard error to log files that the kubelet will then read and manage. Conmon is responsible for managing the lifecycle of the container. So if the container dies, its exit code is given to conmon, its parent, and then conmon writes that to an exit file that then CRI-O reads to know that the container died. And conmon also reports out-of-memory events that the container was killed from So because conmon is there listening on to the container, actually like hanging out with the container, the CRI-O is able to disappear for a second, be restarted, change the configuration variable, whatever, and come back up and then check the state of all the conmons. And that keeps CRI-O nice and slim. We like that. So now for some demos, I'll pass it off to Mrunal.
Right. So here I brought up a local up cluster using CRI-O, and let's see how that actually works. So this is the script I used, and the most important part here is you're setting the container runtime endpoint to point to the CRI-O socket. So that makes the kubelet talk to CRI-O instead of Docker or any other default setup. Now we can examine and see if the node is up. It says it's ready. So we are good to go. So let's start off with a simple Nginx pod first. So it's up and running. Let's try to curl it. We can reach it. Now let's see if we can get logs back from that container. So we will see a get for what we did. Let's try a couple more. And then you can see that it's registering 2 more get requests. So, so that covers like starting a simple pod, just like you would with kubectl. Next example is execing into your pod. So exec is useful for like getting into the namespaces of the pod and examining it. So now we are inside the pod, and this is a view inside that Nginx container. So that covers logging and exec, which are one of the 2 CRI API calls. Let's start another container now. So now I'm running a Fedora shell. And it's up and running. So we're going to attach to it. And now we are inside that container which is running. So Peter talked about how CRI-O ships with fewer capabilities out of the box. So let's take a look at what capabilities are enabled inside this container. So take a look here and then see, let's try, notice that we don't have mknode or either netraw. So let's try pinging the other container and see if it actually works. So it works. So how did that work without capnet raw? So for a moment, we can jump to CRIO configuration. So this is the list of capabilities. So we have dropped capnet raw, but then we are enabling another sysctl that allows us to ping without capnet raw. So you don't have to give it to your containers. Also note here that we are using systemd as a cgroup manager, and that has some advantages in using systemd tools to be able to monitor and take a look at the processes running inside your container. So we talked about SE-Linux. So is anyone here familiar with SE-Linux, how it works? Okay. So SE-Linux is basically assigning process labels and then assigning labels to files, and then there are rules saying which label can access which files. So by default, CRIO will give a unique SE-Linux process label to each container that is started inside a pod. So all the containers in the pod need to be able to talk to each other, so they get the same label, but every pod has a different security label. So for example, this container has this context, and this is the only container / pod that has this context, and its root file system in runc is also labeled with this content. So it can only access the files created for this container. It can't access anything else. Now to simulate a breakout, what I have done here is, for example, say you're running some process, it's root, and it was able to break outside of the container because of a 0-day issue. Now, will it be able to touch your host files? So what I've done here is just bind mounted the etc password to simulate the process being able to somehow see the etc password from the host, and we'll try to access it. Permission denied. So that's SE-Linux in action. Basically, even if your process breaks out of your container, SE-Linux will prevent it from causing harm to other pods, or it will protect the host files from being modified. So we also talked about fork bombs. So let's try that out. Thanks. So I'm trying to launch 50 sleep processes, and note that we are already in a shell. So we were able to launch 49, and the first one is our shell. And why did that happen? Because we make use of a feature in C groups called PID C group limit. So just for demonstration, we set the limit to 50 here, but CRIO ships with a default of 1024. So by default, like, it'll prevent fork bombs from happening, and you can tune that value according to your workload's needs. Next, let's take a look at some of the behind the scenes what's happening. So CRI-CTL. So CRI-CTL is a debugging tool that can talk directly to CRIO to get information back from pods. Like, think Docker PS, what's the equivalent? So there's a CRI-CTL PS. And now we have a web container. So let's try to get more information about it. So we saw that how we are using the systemd as a C group manager. And the advantages is you can do system control status, CRIO, and then specify the ID that you see here, and then you get a nice view of what's running inside your container. And then we also said that conmon is actually the parent process of all the processes running inside any container for CRIO. So how do we get a view of that? Simple. So do CRIO -conmon this, and then you get a view of conmon. Now let's dig deeper. Now you can see how conmon is the parent process for Nginx. So that allows us to basically restart CRIO, and your containers are still up. Like that, nothing happens to that container. You can see that web container is still running. So that allows us to basically update CRIO with some fixes and still not affect your running workloads. And I think that covers the basic operations of what you can do with CRIO. So what we have demonstrated is, like, you can do anything that is expected of a container runtime using CRIO, and you have tools like systemctl and CRI-CTL to be able to debug and dig deeper if you need to understand more. So now we'll open it up to questions. If you want to see anything, or if you have any questions about CRIO, we're happy to answer them.
Just want to understand if CRIO is a runtime or it is not a runtime. Because you say that it calls run C, right?
Yeah, so CRIO is, it implements the container runtime interface. CRIO calls into container runtimes. Technically, you could more call it a container manager, but sometimes container runtime and container manager is interchangeable because it's not many people use the term container manager, so it's container runtime is kind of all encompassing. But
yeah. So at the lowest level, like runc implements the code which is calling into the system calls for spawning a container process, like setting up the C groups, unsharing the namespaces, and so on. But CRIO is doing more. It's also managing your images, and it's basically satisfying the requirements of the kubelet. It's like think of it as a orchestrator, like container orchestrator rather than a low-level runtime.
It's like the middleman between the kubelet and the runtime.
Yeah.
More questions?
This is in continuation to some of my questions that I asked offline as well. So just wanted to understand more on the differences between how CRIO is used versus containerd. Because if I were to use containerd instead of CRIO, I would use a containerd shim and then it would talk to container D, and then it would do. So I'm thinking of CRI-O as here a better replacement to using container D in that fashion. So would be glad if you could elaborate more on this.
So technically, container D and CRI-O operate in the same space, and container D will also need a CRI implementation, which is what you're referring to as a shim. But
Yes.
CRI-O, being Kubernetes focused, doesn't have that additional layer. We are just implementing the CRI directly, and because we don't care about any other clients. So that hop is reduced, and out of the box, support for SLNX and other features is better. And one more thing I would call out is our container monitor conmon is written in C to be efficient, and also since we are the way OCI runtimes work, you always need a container monitor process. And when you're running, say, 100 pods, you're talking about 200 containers and 200 instances. The advantage of writing it in C is you can dynamically link to the library, so your memory per process overhead for the conmon process is very low, even when you have a lot of containers and pods running.
Thanks. Would you know how container D would monitor the container data?
Last I looked, there was a shim, but which is in Go, I think.
Okay. Okay. All right. Thanks.
Any more?
Yes. Excuse me.
So I guess my question's about stability and scale. Like we run large shared clusters, and we have problems with the stability of our runtime. Like when we get situations where nodes just can no longer schedule pods and things, and we use Docker, and we're considering using CRI-O. Is there something about the architecture that should provide more stability?
So I think we also at Red Hat have ran Docker in production, and we learned lessons there with issues that we saw at our customer space, and designed CRI-O from the beginning to address those problems. For example, CRI-O is very Kubernetes focused, right? So one operation that the kubelet does frequently is list everything, list the containers again and again. So we wanted to make sure that that operation is very fast. So we do a lot of caching in that layer, so we don't have to call to get the runtime state unless absolutely needed. And then we get the state asynchronously using inotify when conmon writes the exit file. So we kind of learn lessons from running Docker in production and design CRI-O to do better than Docker. Our pleg numbers are better than Docker. Since we now run CRI-O in production at Red Hat in 4x, so we have that comparison. And the things like being able to update CRI-O without affecting the workloads and so on. So I would encourage you to give it a try. And
do you run it with RunC? What's your preference for runtime?
yeah, so we use RunC right now, but we are looking into running Kata in production as well. And the use cases we think Kata would work very well is where you want strong isolation between clients. If you're trying to do multi-tenancy, or if you're trying to do privileged operations, you want to do builds inside your pods, then you would want to give more capabilities to your pods, and having that VM isolation makes sense for such use cases.
Oh, yes.
Yeah, thank you for the presentation. You mentioned that you didn't implement copying files into the container with CRI-O. Does that affect either kubectl or OC rsync or CP functionality?
No, all of those work. So those features work. But as you know, the Kube's CTL CP has had a lot of security issues over the past years, and there's some proposals to just get rid of it entirely. Yeah. So those operations should still work.
So potentially dumb question, but when the container crashes really often and very fast, you often can't get any logs. So if you're using CRI-O instead, would that help?
So I think that there's a Kubernetes level, kubelet level setting, and it will retain the 1 or 2 last containers. So you can still access the logs from the previous crashed instance.
So if the container is crashing, like if the process is crashing very quickly, then it doesn't retain anything. That's what we've observed.
Oh, okay. So you're talking about the case where you can't even, it's not even
Yeah.
getting to the point where it is logging. It's just,
Where it is in STD also, if you're lucky enough to have exec in or be live at that point, it'll capture it, but it cycles so fast that.
yeah. So I think like for debugging such cases, you would probably do a development mode debugging rather than trying to do it. It'll be easier to say use like Podman locally and debug that issue where you have more control over the logs. And I think we are also looking into adding an strace based plugin, so that can help with debugging like crashing containers.
Okay.
So,
Yeah, I'm asking from an infrastructure point of view. So like we don't own the containers, but we're just running them for our workloads, right? And then something is crashing and he's like,
right.
I don't see any logs, so it must be your fault.
Right. Yeah, no, that's a good question. And I think like having an strace like plugin will help there, where we can strace the container and try to capture the strace output somewhere to debug crashing
Cool, thank you.
containers. Yeah.
Do you have any idea of metrics in terms of overhead that you would save using CRI-O versus Docker?
So the plague numbers are way better. So I don't have numbers off the top, but I think we can work to share them with our performance team. And what I would like to mention one more thing. So we are working on a feature for 117 where we get rid of the pause container entirely. There's like no pause unless you're sharing the PID namespace. So that will further reduce the memory overhead per pod in CRI-O.
So simple, stupid question of if I go on a CRI-O node, a node that's running CRI-O right now in Kubernetes, and I do a Podman PS, I see nothing. But if I do a CRI-CTL PS, I see everything. So I'm wondering what the difference is in the back end of that.
Sure. So right now, the status is that Podman and CRI-O are integrated at the container storage level. So if you pull an image with Podman, CRI-O can see the image, but we haven't integrated at the runtime level. And like that is one of our top priorities to get both of those integrated. So I expect that within the next few months, you'll see progress over in that area where Podman can see CRI-O containers. So you can potentially use Podman to exec and debug containers started by CRI-O.
Thanks for the presentation. You mentioned that version can be upgraded without disrupting the pods. Is it true for the major version upgrades, minor, or both?
So I think it depends on like if CRI introduces a breaking change or not. So if there's no CRI breaking change, then you should be able to just replace the CRI-O binary and restart it.
So we don't need to cordon or drain the node, just.
No, you shouldn't be, because like your containers are still running, and when CRI-O comes up, it reconciles the state which what is already running, and it's able to respond to the kubelet.
Thanks.
Yeah.
And I'm also pretty sure, following up, that CRI tries really hard not to introduce N-1 incompatibility changes. So typically, like kube +1 should work with CRI-O. That's not super guaranteed. We don't guarantee that, but we don't test it, but it should.
That's awesome. Quick follow-up to that, which is the same true for config changes, that they might not require a daemon restart for CRI-O?
So we have since about 1.14, we are now at the point where a rollover of the CRI-O binary can do an N-1, work with the CRI-O config. You would need to then replace the CRI-O config because we don't guarantee N-2. But right now we do test that for our own production. We do have that.
Sure, but for most settings, like if I just go change some setting that I want to run differently in production, will CRI-O just pick that up, or does it require a restart?
So Sasha, who is also a CRIO maintainer, has been recently adding features where we can make changes to some CRIO configuration, and you can send a SIG hub to CRIO and it will pick up those changes. So the goal is to support that for as many configuration settings as possible. And another thing that we are working for is like baking the defaults into the CRIO. So basically, your CRIO.conf should be totally commented out, and it should have great defaults, and you should have a very good reason to try and change something. So that makes it very easy to not introduce like breaking changes and configuration when you are moving from one version to the other.
Very cool.
Sorry, a follow-up question. You guys introduced CRIO Wipeout service in 1.13 or 1.14. So what is the benefit out of it? Like you're deleting everything?
Yeah. So that shouldn't technically be required. So, but now I'm going to like OpenShift land. In OpenShift land, it made sense for us to wipe out the node completely, because when the way we do upgrades, we are always pulling new images. So all the old images weren't needed anymore. So that service, I think, should be optional if it isn't, but that's why it was created for. Basically, just remove all the images, because we know for sure that when we are going to upgrade a node, we are going to repull all the images.
So again, that will require cordon and drain?
Yes. So yeah, that upgrade, like a cluster upgrade, will require draining and all that stuff. Yeah.
But it's optional. It's not.
Yeah, it's optional. I mean, you don't have to reboot it, but that's how OpenShift does it.
Yeah. So that's more of an OpenShift specific thing, but you can optionally include it if you want to.
Are you looking for any help in terms of contributions, whether it's just testing or?
Absolutely. Like contributors are super welcome. We always have like a bunch of things to do, and we feel short-handed with the amount of things that is going on. So you're welcome to like ping us on Slack or just open an issue, or we are happy to point you to where we could use help.
Great.
Yeah.
We got any others? Am I missing?
All right, thanks for joining the talk. And I would also like to say that we have a more advanced talk tomorrow. Like if you want to go further into how the CRI calls are working and so on, we'll be diving in deeper if you want to understand more.
Thank you for joining.
All right.